Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So I want you to just imagine for a second stepping outside on a really crisp, clear night.
The kind where the stars just kind of pop.
Exactly. And you look up and you find the constellation Orion.
Right. Highly recognizable.
Yeah. And you look at Orion's right shoulder, that glowing kind of reddish-orange dot.
Betelgeuse.
Betelgeuse, right. Humanity has been staring at this specific star for millennia, but it turns out it's been keeping this absolutely massive secret.
A really massive one, yeah.
I mean, think about it this way. If you took our sun, the blindingly bright center of our entire solar system, and you just dropped it right next to Betelgeuse, our sun would be completely invisible.
Entirely erased by the glare.
Right. You wouldn't be able to see it with the naked eye, and honestly, you would struggle to see it with our most advanced telescopes, which kind of explains this really uncomfortable reality in modern astronomy.
It's very humbling, honestly.
Totally. For the last 100 years, a massive star, up to 3 times the size of our sun, has just been hiding in plain sight, right there, orbiting Orion's shoulder.
And we didn't definitively find it until right now.
It's wild. So today, we're unpacking the stunning conclusion to this century-long astronomical quest. We are breaking down the definitive discovery of Betelgeuse B.
The hidden companion star.
Yeah, the hidden companion. We're going to track the historical suspicions, like why we even thought there was a hidden star in the first place.
Right, because the clues were always there.
Exactly. And we'll analyze the mechanics of that crazy false alarm from a few years ago.
Oh, the great dimming. When everyone thought it was going to explode.
Yes, when everyone was panicking about a supernova. And then we're going deep into the specific optical physics and the planet hunting technology that finally allowed astronomers in the Atacama Desert to capture a direct image of this thing.
Because the implications here, they go far beyond just solving an old mystery.
Oh, for sure.
Finding a companion star of this magnitude, hiding in the glare of a highly evolved supergiant, it introduces a whole new set of incredibly high-stakes physics. Right. The eventual death of Betelgeuse, which we know is coming, is going to be fundamentally altered by the presence of this neighbor.
So to understand why finding Betelgeuse B is such a massive paradigm shift, we really have to establish the baseline of Betelgeuse itself.
Yeah, we have to talk about the scale.
The scale is just, it's hard to wrap your head around. The reason astronomers have spent nearly a century frustrated by the star comes down to sheer physical dominance. It's a red supergiant.
Right.
If you dropped Betelgeuse into the center of our solar system, its surface would extend out past the orbit of Jupiter.
Swallows everything.
Yeah. Mercury, Venus, Earth, Mars, the asteroid belt, all completely gone inside the star.
And that scale dictates everything about how we observe it. We are dealing with a bloated, highly evolved star that's in the final stages of its life cycle.
Right. It's running out of gas.
Exactly. And because it's so massive and relatively close to us, I mean, roughly 650 light years away, it is one of the brightest objects in our sky.
With that really unmistakable reddish-orange color.
Right. But the defining characteristic of Betelgeuse, the quirk that caught the attention of everyone from ancient Aboriginal astronomers to, like, Sir John Herschel in the 1830s, is its variability.
It doesn't just sit there.
No, its brightness is not constant.
It dims and brightens. And the crucial detail here, the thing that really kicked off this whole century-long hunt, is that it doesn't just flicker randomly. There's a rhythm to it.
Yeah, in astrophysics, when you plot a star's light curve, you know, the graph of its brightness over time, and you see a repeating, predictable variation, it's a massive red flag.
It signals a mechanical cycle.
Exactly. A star of that magnitude doesn't just change its luminous output on a strict schedule without a physical driver.
Think of it like this. Say you look out your window, right? And the streetlight at the end of your block is flickering.
Just completely randomly.
Yeah. If it's random, you just assume the internal mechanism is breaking down. It's a dying bulb. But if you sit there with a stopwatch and you time it, and you realize that streetlight is dimming on a precise, predictable schedule, like, say, every 400 days, like clockwork, you stop blaming the bulb.
Right. You assume someone is messing with the power.
Exactly. You assume a neighbor is routinely tapping the power line. And for roughly a century, astronomers looking at the periodicity of Betelgeuse's brightness suspected a stellar neighbor was tapping the line.
Right. The hypothesis was that as a smaller companion star orbited the supergiant, its gravity would tug on the larger star.
Or maybe it was periodically passing through the outer layers of the supergiant's extended atmosphere.
Yeah, exactly, creating those rhythmic dips in the light we receive on Earth.
But the frustration here, like the maddening part for astronomers, is the gap between mathematical suspicion and visual confirmation.
Oh, it's the worst.
You can have the light curves, you can track the scheduled flicker, but no matter how much you upgrade your lenses, the culprit remains completely invisible.
Because of the sheer luminosity of Betelgeuse. I mean, the supergiant is pumping out something like 100,000 times more photons than our sun.
That's just...
But it's blinding.
Yeah.
That contrast ratio is the primary enemy of observational astronomy. When you're trying to image a faint object next to an incredibly bright one, the photons from the bright object literally spill over the pixels on your detector.
It just washes out the faint signal entirely.
Completely. So the companion was basically trapped in the mathematical realm. We could see the gravitational footprints it was leaving on Betelgeuse, but we couldn't actually see the star making them.
Okay, let's actually get into the mechanics of those footprints. Because before they get the direct image, they knew something was there through something called radial velocity.
Right.
So how exactly does a hidden star leave a measurable footprint in the light of the main star?
It really all comes down to the Doppler effect, but applied to starlight.
Okay, like a police siren changing pitch when it drives past you?
Precisely. So when two stars orbit each other, they don't actually just have one sitting still while the other goes around it. They orbit their common center of mass, which we call the barycenter.
Right.
Now, even though Betelgeuse is immensely massive, the companion still exerts a gravitational pull on it. And this causes Betelgeuse to wobble slightly as it moves through space.
So they're both doing this kind of slightly off-center waltz together?
Exactly.
Yeah.
And we can measure that wobble using spectroscopy. We take the light from Betelgeuse and we spread it out into a spectrum like a rainbow.
Like shining it through a prism.
Right. And in that spectrum, there are dark lines, absorption lines, that are created by specific elements in the star's atmosphere absorbing specific wavelengths of light.
Like a barcode.
Perfect analogy, yeah, a barcode. As Betelgeuse wobbles toward Earth, those barcode lines shift slightly toward the blue end of the spectrum because the light waves are getting compressed.
And then as it wobbles away from us,
The lines shift toward the red end because the waves are getting stretched out.
so by meticulously tracking how those dark barcode lines slide back and forth, over decades of observation, astronomers could calculate the exact gravitational pull required to cause that specific wobble.
Exactly. They basically mapped the invisible orbit. They could determine the orbital period, the eccentricity of the orbit, and theoretically, the mass of the hidden companion that had to be causing the wobble.
Okay, but wait, I'm going to push back on this right here.
Sure.
You just said they used this radial velocity data to calculate the mass of the companion. And based on that math, for years, the astronomical community predicted the companion would be roughly one solar mass, so about the size of our sun.
Right.
But the brand new discovery that we're talking about today confirmed the star is actually 2 to 3 times that mass.
Yeah, much bigger.
So how can the spectroscopic math be so perfectly accurate about the orbit and the location, but miss the actual mass of the object by a factor of 3?
That points to one of the most notorious ambiguities in all of astrophysics. It's called the inclination angle, or often the sine degeneracy.
Okay, break that down for us. Why does the angle matter so much?
Well, radial velocity only measures movement along our specific line of sight. So directly toward us or directly away from us.
Right.
It tells us absolutely nothing about the star's movement up, down, left, or right across the sky.
Okay, so imagine you're looking at a merry-go-round.
Yes, perfect.
If you're looking at it perfectly edge-on, you can clearly see the horses moving directly toward you and directly away from you.
Exactly. That is a 90-degree inclination. You're getting the full velocity measurement.
But if I'm hovering in a helicopter, looking at that same merry-go-round from directly above, so a 0-degree inclination,
Yeah.
the horses are just moving in a circle across my field of view.
They are never moving toward you or away from you.
Right.
And therefore, your radial velocity measurement would be 0, even though the merry-go-round is spinning rapidly.
Oh, wow.
Yeah. So when we look at a binary star system out in deep space, we almost never know the exact tilt of the orbit relative to Earth. The spectroscopic wobble only gives us the minimum possible mass of the companion.
Because if the orbit is tilted relative to our line of sight, the true mass has to be higher to produce the wobble we're measuring.
You nailed it. The astronomers who predicted a one solar mass companion assumed a fairly edge-on orbit. But because Betelgeuse B turned out to be nearly 3 solar masses, we now know the orbit must be significantly tilted.
So the math wasn't wrong, it was just incomplete due to our fixed vantage point in the cosmos.
Exactly. We're stuck here on Earth.
It's fascinating how a physical limitation of our perspective entirely masked the true nature of the star for 100 years.
It really is.
And it's wild because just as researchers were aggressively dialing in on these orbital predictions, Betelgeuse decided to throw this massive curveball that derailed the hunt and triggered a global panic.
Oh, yes.
We have to talk about the Great Dimming.
This is such a critical chapter in the story because it highlights just how volatile red supergiants are, and it perfectly sets the stage for the specific team that ultimately found the companion.
Right, so a few years ago, Betelgeuse underwent this completely unprecedented drop in luminosity.
It was visible to the naked eye. Anyone could go outside and see it.
The star lost a massive fraction of its brightness in a matter of weeks. And I remember the absolute frenzy in the astronomical community.
Oh, Twitter was going crazy.
Because Betelgeuse is a known ticking time bomb. It has exhausted the hydrogen fuel in its core, it's burning heavier elements, and it is on a one-way trip to a core collapse supernova.
Right. And when a star with that specific doomed profile suddenly drops in brightness, the immediate assumption is that the engine is failing.
Core is destabilizing.
Exactly. The explosion is imminent.
So the scientific tension centered on whether we were witnessing an intrinsic change or an extrinsic change, right?
Yes. An intrinsic change would mean the internal thermodynamics of the star were actually failing. Like perhaps the outward radiation pressure that holds the star against its own gravity had suddenly dropped.
Which is the precursor to collapse.
Exactly. But an extrinsic change would mean the star's internal engine was totally fine, but something physical had moved between the star and our telescopes, basically blocking the photons.
So to solve this, French researcher Miguel Montarget and his team secured observation time on the Very Large Telescope, the VLT, down in Chile.
Right.
And they didn't just measure the light, they actually managed to resolve the surface of Betelgeuse to see what was happening.
Which is incredible. Resolving the surface of any star other than our own sun is an extreme technical achievement.
Because they're usually just points of light, right?
Yes, even the biggest telescopes usually just see a dot. But because Betelgeuse is so physically massive and relatively close, the VLT could capture its actual disk.
Wow.
And what Montarget's team discovered debunked the supernova panic completely. The dimming was not an internal collapse. It was a massive, localized, extrinsic block.
They found out the star had essentially burped out a massive cloud of gas.
Yeah, a huge burp. We need to look at the flow dynamics of a red supergiant to understand how violent that burp actually was.
Okay, set the scene.
So unlike our sun, which has millions of relatively small convection cells boiling on its surface, kind of like a pot of boiling water, a bloated supergiant like Betelgeuse has convection cells that are just staggeringly huge.
How huge?
A single one can cover a huge fraction of the star's entire surface. We are talking about bubbles of boiling plasma the size of our inner solar system.
Wait, really? Just one bubble?
Just one bubble, rising from the interior, releasing heat and sinking back down.
Okay, so one of these colossal convection cells breaches the surface and violently ejects a massive plume of stellar material deep into space.
Yes. A massive bubble of hot gas is blown off the star. And as this plume travels rapidly away from the intense heat of the photosphere, the thermodynamics drop sharply.
It cools down?
It cools down very fast. And when stellar gas, which contains elements like silicon, oxygen, and carbon, cools past a specific temperature threshold, it undergoes a phase change. The gas condenses into solid particulates.
So it quite literally turns into rock and soot in the vacuum of space.
Exactly. It forms silicate dust.
Yeah.
And this immense cloud of newly formed dust happened to condense directly in our line of sight, physically eclipsing the southern hemisphere of the star.
Unbelievable.
It absorbed the visible light from Betelgeuse and re-emitted it in the infrared, which caused the dramatic dimming we saw on Earth.
It basically created its own eclipse.
Yeah, no supernova, just localized atmospheric chaos resulting in a dust cloud.
Now, while that might have disappointed the people hoping to see a star explode in our lifetime, the scientific yield from that event was vital.
Oh, absolutely crucial.
Because it forced Montarget and his team to become intimately familiar with the optical quirks of Betelgeuse.
Right. They learned how to handle the overwhelming glare of its surface how to process the noise in the data, and how to push the VLT to its absolute limits.
They basically forged the exact specific skill set required to hunt down the companion star.
Exactly. And once the dust cleared, literally the focus shifted back to that century-old mystery.
Because the periodicity was still there?
Still there.
The radial velocity wobble was still there, but they needed a highly specific window to actually attempt a direct observation. You can't just point the VLT at Betelgeuse on a random Tuesday and hope to spot the companion.
No, you need a treasure map.
Right. And in 2024, 2 robust astronomical studies essentially provided that map.
They synthesized decades of astrometric and radial velocity data. By meticulously mapping the gravitational wobble we talked about, they reconstructed the invisible orbit.
They didn't just confirm the companion's existence, they calculated its exact orbital trajectory.
Yes, and they predicted that in December of 2024, the companion would reach a very specific geometric point known as maximum elongation.
Okay, this is the critical physical concept that made the discovery possible. Let's map out maximum elongation for everyone. Why does the physical distance, the visual separation from the main star, dictate whether or not we can see it?
It comes right back to the contrast ratio and the physical limits of our optics. The angular separation between the primary star and the companion, as viewed from Earth, is incredibly small.
Because they're 650 light years away.
Exactly. So when the companion is moving through the part of its orbit that brings it in front of or behind Betelgeuse, the angular separation is virtually zero. The light of the companion is entirely swallowed by the diffraction halo of the supergiant.
It's like trying to spot a single faint firefly buzzing around a massive stadium floodlight.
Perfect.
If the firefly is hovering just an inch from the glass of the floodlight, it is completely consumed by the glare. You have absolutely zero chance of resolving the light of the insect against the millions of lumens pouring out of the bulb.
Right.
Your only hope is to wait for the exact moment the firefly flies a few feet away from the bulb, out toward the very edge of the floodlight's beam.
And maximum elongation is that exact moment. It is the point in the orbit where the physical geometry places the companion at its widest possible apparent distance from the primary star. From our perspective here on Earth.
It maximizes the angular separation.
Yeah.
So the 2024 mathematical models basically provided Montarja and his team with a definitive deadline. They mapped the orbit and said, the firefly will be at the edge of the floodlight's beam in December 2024. If you want to take a picture, this is your only window before the orbit carries it back into the glare.
Yeah, we gave them the win. But knowing when to look is useless if you lack the optical hardware to overcome the fundamental physics of light diffraction.
Which is where the story shifts to the engineering marvel of the VLT and a specific instrument called SPHERE.
Yes.
Let's break down the VLT, the Very Large Telescope, located in the Atacama Desert in Chile. The location itself is basically half the technology, right?
Oh, absolutely.
Yeah.
You need an environment that removes as much of Earth's atmosphere from the equation as possible.
Because atmosphere is the enemy of astronomy.
The Atacama is one of the highest, driest environments on the planet. Atmospheric water vapor absorbs light, and atmospheric turbulence, hot and cold pockets of air mixing together that bends and distorts starlight.
It's what causes stars to twinkle.
Right. And for an astronomer trying to resolve a faint companion star next to a supergiant, twinkling is catastrophic. It smears the light all across the detector.
But even in the Atacama, you still have some atmosphere to punch through. You're not in space. And more importantly, you still have the overwhelming blinding glare of Betelgeuse itself to deal with.
Which is where the SPHERE instrument comes in. Anthony Bacaletti, a co-author on the new study, pointed out something really fascinating. SPHERE was not designed to look at aging supergiants.
No.
No, it is an exoplanet hunting tool.
Oh, wow. So they repurposed it.
Yeah, but the crossover in application is brilliant. Finding a Jupiter-sized planet orbiting a distant star presents the exact same optical challenge as finding a massive companion star orbiting an impossibly bright supergiant.
Because in both cases, the primary star is billions of times brighter than the target.
Exactly. To reveal the target, you must artificially suppress the light of the primary star.
But how exactly does SPHERE suppress the light of a star that bright without blinding the rest of the image? I mean, I know we can block light physically, like holding your hand up to the sun to see an airplane.
Sure.
But at an astronomical scale, diffraction must cause the light waves to bleed around the edges of whatever block you use, right?
Yeah.
How do they solve the physics of the light bending around the mask?
That is the defining genius of a coronagraph, which is the absolute heart of the SPHERE instrument. It doesn't just use a simple physical block. It uses a series of highly engineered optical masks and stops to actively manage the diffraction of light waves.
Okay, walk me through this. Walk through the path of the light as it enters the telescope.
Right. First, the light from Betelgeuse enters the primary mirror of the VLT. But before it reaches the coronagraph, it passes through an adaptive optics system.
Okay, to fix the twinkling.
Exactly.
Yeah.
This is crucial for correcting that atmospheric smearing we just discussed. The VLT actually fires a powerful laser into the upper atmosphere.
A laser.
Yeah, it excites sodium atoms in the mesosphere to create an artificial guide star.
A fake star they use as a reference point.
Exactly. And a sensor measures exactly how the atmosphere is distorting the light of that artificial guide star thousands of times a second.
That's crazy fast.
It has to be.
Yeah.
It feeds that distortion data to a deformable mirror inside the telescope. This mirror has hundreds of tiny actuators behind it that physically change the shape of the mirror surface in real time.
Wait, they bend the mirror?
They constantly ripple and bend the glass, perfectly countering the atmospheric turbulence. It essentially flattens the light waves back out, removing the twinkle entirely.
So now you have a perfectly sharp, pristine beam of light from Betelgeuse entering the coronagraph.
Yes. And the beam hits a focal plane mask. This is a tiny opaque dot precisely aligned to block the central core of Betelgeuse's light.
The hand blocking the sun.
Right. But as you pointed out, light acts as a wave. When it hits the edge of that opaque dot, it diffracts. It bends around the mask, creating a series of bright concentric rings called an airy pattern.
So it leaks.
It leaks badly. If you stop there, those diffraction rings will completely wash out the companion star.
The light bleeds over, so how do you clean up the bleed?
The light passes through a second lens, which refocuses the beam, and then it hits a light stop.
A light stop.
Yeah, it's a highly specific aperture placed further down the optical path that is mathematically designed to block those diffracted light rings while letting the rest of the light pass through. It essentially clips the noisy edges off the light beam.
You are physically stripping away the glare layer by layer using wave optics.
It's unbelievable engineering.
Yeah.
But even with adaptive optics and a perfect coronagraph, the suppression is never 100% perfect.
There's always some noise left over.
Always. There are microscopic imperfections in the mirrors, slight thermal shifts in the instrument itself, resulting in a residual halo of scattered light. We call it speckle noise.
And let me guess, these speckles can look exactly like a faint companion star.
Exactly like it. So when Montargis and his team looked through Sphere in December 2024, during that maximum elongation window, they don't just see a clean image of Betelgeuse B sitting there in the dark.
They just see static.
They capture the raw data, which looks like a chaotic, noisy halo of residual light. The actual discovery happens during the post-processing phase, which takes months of intense computational labor. Months. They use a technique called angular differential imaging, or ADI.
How does ADI separate the fake speckles of noise from the actual light of the hidden star?
It's actually brilliant. It exploits the rotation of the Earth.
Okay, how?
As the telescope tracks Betelgeuse across the sky over several hours, the optical field of view naturally rotates relative to the instrument itself. This means the actual astrophysical objects, like the companion star, will slowly rotate through the field of view over time.
But the optical imperfections, the speckles caused by the telescope's own mirrors...
They stay fixed in place relative to the detector.
Oh, that is so smart.
Isn't it? By taking hundreds of images over several hours, astronomers can run complex algorithms that isolate the static noise and literally subtract it out of the sequence.
Wow.
Once you peel away the static speckle noise, the true light of the companion star, which rotated with the sky, is finally revealed.
I really want to focus on the psychological weight of those months of data processing for a second.
It must have been excruciating.
Right. You are Miguel Montargis. You use the exact window predicted by the 2024 orbital models. You used Sphere, the most advanced coronagraph on the planet. But you also know that for 100 years, this star has defeated every single astronomer who tried to find its companion.
Every single one.
And you were sitting at a computer running ADI algorithms, ruthlessly doubting your own findings, wondering if a speck of light on the screen is a thermal artifact or a century-old ghost.
The rigor required in that phase is immense. You have to prove to yourself that you haven't just manufactured a star out of statistical noise. You have to be your own harshest critic.
Until the final algorithm finishes, and the residual light of Betelgeuse is completely digitally subtracted. And there, sitting in the dark space, exactly where the math predicted it would be, is a distinct, undeniable source of light.
And Montargis actually described his reaction to seeing the final processed image. He said he jumped from his chair.
I would have screamed.
It is the ultimate vindication of predictive science. The light of the companion star, traveling across 650 light-years of space, finally extracted from the glare by human engineering.
But the discovery immediately pivoted from a technological victory into a massive scientific shock.
A huge shock.
Because they found it, yes, but the reality of what Betelgeuse B actually is wildly contradicted the long-standing theories.
Oh, totally. Threw the models out the window.
Yeah, Montargis admitted he honestly didn't think Sphere had the sensitivity to detect the star based on those earlier predictions.
Because the predictive math was flawless regarding the location of the companion, but it was drastically wrong about the nature of the companion.
Right.
If Betelgeuse B had been a one-solar mass star, as the radial velocity models initially suggested, its luminosity would have been too faint to pierce through the residual speckle noise, even at maximum elongation.
Even with all that incredible tech.
Exactly.
So why could they see it?
Because it wasn't one solar mass. The VLT data confirm that Betelgeuse B is actually 2 to 3 times the mass of our Sun.
That is a massive difference.
It really is. The increase in mass corresponds to an exponential increase in luminosity. It was significantly brighter than anyone anticipated, pushing it above the detection threshold of the Sphere instrument.
Which goes right back to your point about the orbital tilt, the sinus degeneracy.
Exactly.
Because the orbit was highly tilted relative to Earth, the actual mass had to be much higher to produce the wobble we measured.
Precisely. And finding a 3-solar mass star hiding next to Betelgeuse forces a total recalibration of our understanding of the entire system. Now, there were previous hints, like a possible direct detection using the Gemini North Telescope in Hawaii.
But it wasn't definitive.
Right. This Sphere image is the definitive proof. It completely removes the ambiguity.
Let's grasp the sheer scale of this again. A star 3 times the mass of our entire sun has been hiding in plain sight for a century. I mean, if you replaced our sun with Betelgeuse B, the Earth would be instantly vaporized.
Instantly.
It is a massive, intensely bright star in its own right. How does something that massive remain hidden?
It just highlights the monstrous immensity of the primary star. Yes, Betelgeuse B is highly luminous, but Betelgeuse itself is emitting roughly 100,000 times more light.
It's like trying to hear a whisper next to a jet engine.
Exactly. Even a 3-solar mass star is completely lost in that deluge of photons. You think you understand a stellar neighborhood because you've observed it for hundreds of years, and then you discover a mansion hidden behind a billboard you never managed to look around.
Okay, so we have definitively found the hidden companion. We know its mass, its orbit, and its reality. But in astrophysics, answering a century-old question immediately spawns a drastically more complex set of physical problems.
Oh, absolutely. The future of this system is fascinating.
Because we have to look at the future of this binary system. But before we get into the explosive stuff, we should mention the caveats, right?
Yes, rigorous scientific caveats first. The team notes that to achieve absolute certainty regarding the exact orbital mechanics, they do need to observe it again in a year or so.
When the orbit carries Betelgeuse B to the opposite side of the supergiant.
Right, tracking it across multiple points in its orbit locks in the kinematics. However, as Montargis stated, there is very little space left for doubt.
Okay, so assuming Betelgeuse B is exactly what this data shows, we face a monumental physical dilemma.
We do.
Betelgeuse is an evolved red supergiant. It is on an irreversible path to a core collapse supernova. How does the confirmed presence of a massive 3-solar mass companion star alter the explosive fate of the supergiant?
It changes the entire paradigm of stellar death for this system.
Because it's not alone anymore.
Exactly. When a single isolated massive star goes supernova, the physics are relatively straightforward.
Straightforward for a supernova anyway.
Fair point, yeah. But basically, the core runs out of nuclear fuel, the outward radiation pressure stops, gravity takes over, and the core collapses inward at a fraction of the speed of light.
Just a catastrophic freefall.
Right. The core compresses until it hits quantum degeneracy, basically bounces off itself, rebounds, and sends a shockwave outward that blows the outer layers of the star into a spherical expanding nebula.
But when you introduce a massive companion star into the immediate vicinity,
the dynamics of that collapse become infinitely more chaotic.
We enter the realm of binary stellar evolution.
Yes. And the most critical factor here is gravity, and a concept known as the Roche lobe.
Okay, let's explore the Roche lobe. How does gravity fundamentally alter the shape and behavior of the supergiant before it even explodes?
Well, in a binary system, each star exerts a gravitational pull. The Roche lobe is basically the teardrop-shaped region of space around a star where its own gravity is dominant over the companion's gravity.
It's like a gravitational boundary line.
Yes. When Betelgeuse was a younger, smaller star, it sat comfortably deep within its own Roche lobe.
All of its gas and plasma were securely bound to its own gravitational center.
Exactly. But as it evolved into a red supergiant, it expanded massively. Its outer atmosphere puffed up to an incredible degree.
Right.
Now, if the outer layers of Betelgeuse expand so much that they breach the boundary of its Roche lobe, the material is no longer gravitationally bound to the supergiant. It crosses the tipping point.
Which is the L1 Lagrangian point, right?
Yes, the L1 Lagrangian point.
Yeah.
At that point, the gravitational pull of Betelgeuse B actually takes over.
Oh, wow.
The 3 solar mass companion can begin actively stripping the outer layers of hydrogen away from the dying supergiant. We call this Roche lobe overflow, or mass transfer.
So the companion is essentially cannibalizing the supergiant's atmosphere before the core even collapses.
Actively pulling material onto itself, yes.
How does stripping those outer layers change the mechanics of the eventual supernova?
It can fundamentally alter the classification in the light curve of the explosion.
Okay, how so?
If a red supergiant explodes with its massive outer envelope of hydrogen mostly intact, it typically produces what we call a type IIP supernova. The P stands for plateau.
Meaning the brightness stays stable for a while.
Exactly. The explosion stays incredibly bright for months as the shock wave slowly pushes through that thick, dense hydrogen envelope.
But if Betelgeuse B has stripped a significant portion of that hydrogen envelope away beforehand,
then the shock wave encounters much less resistance. You might get a totally different light curve, potentially closer to a type IL, or even pushing toward a stripped envelope supernova if enough mass is transferred.
so the neighbor changes the whole explosion profile.
Right. The total mass of the star at the absolute moment of core collapse dictates how the explosion unfolds, how bright it gets, and what specific heavy elements are synthesized and ejected out into the interstellar medium.
Let's use an analogy for this. Imagine you are watching the scheduled demolition of a massive, derelict skyscraper.
Okay, I'm picturing it.
You have the blueprints, you know exactly where the demolition charges are placed, and you can calculate exactly how it's going to fall into its own footprint. It's a known quantity.
Very predictable.
But right before they push the plunger, you suddenly realize there is a highly pressurized, fully fueled gas station sitting directly on the property line, deeply entangled with the structural supports of the skyscraper.
Oh, that's a brilliant way to put it.
The demolition is still going to happen, right? The core collapse is inevitable. But the dynamics of the fall, the structural integrity of the outer walls, and the ensuing shock wave just became infinitely more unpredictable because of that massive gravitational anchor sitting next door.
Exactly. Which brings up the ultimate question regarding the fate of Betelgeuse B itself.
Yeah, what happens to the neighbor? When the core of the supergiant collapses and unleashes literally the most violent event in the universe, what happens to the companion star sitting right in the blast zone?
This is one of the most intense areas of study in binary astrophysics right now. The survival of the companion depends on several factors. Its orbital distance at the absolute moment of explosion, its own density, and the sheer kinetic energy of the supernova ejecta.
Is it possible the shockwave vaporizes the companion entirely?
Vaporization of a 3 solar mass star is unlikely, given its own significant gravitational binding energy.
So it'll survive, but
the supernova shockwave slamming into the companion will cause extreme structural damage. It will likely strip away the outer layers of Betelgeuse B, injecting massive amounts of heavy radioactive elements from the supernova directly into the companion's atmosphere.
just blasting it with radioactive shrapnel.
Essentially, yes, it will heavily pollute the surviving star.
But beyond the physical damage, the orbital mechanics completely shatter.
Instantly. This is what we call the slingshot effect.
Right now, Betelgeuse B is being held in orbit by the immense gravitational mass of the supergiant.
Yes. But when the supernova occurs, the primary star ejects a massive percentage of its total mass outward at significant fractions of the speed of light.
The gravitational anchor just disappears almost instantaneously.
And because of the conservation of momentum, Betelgeuse B will no longer have a central mass to orbit. It's just gone.
So what does it do?
It will continue moving along its orbital trajectory at whatever velocity it had at the exact moment of the explosion. It will literally be launched out of the binary system like a cannonball.
It becomes a runaway star.
Exactly. Depending on its orbital velocity, it could become a hypervelocity star, shooting across the galaxy entirely unbound from its previous neighborhood.
That is wild to think about.
The discovery of this hidden companion has provided astrophysicists with the ultimate real-time laboratory to study the chaotic interplay of mass transfer, orbital dynamics, and stellar death at the extreme edge of physics.
It's just the scope of this entire journey forces a complete shift in perspective.
It really does.
I mean, we began with a brilliant, blinking red dot in the winter sky, observed by generations of ancient astronomers who carefully tracked its rhythmic variations.
Just using their eyes.
Right. And then we moved through a century of mathematical frustration, watching light curves and radial velocity wobbles, mathematically proving a ghost was in the machine, but lacking the optical hardware to actually see it.
Then we analyzed the fluid dynamics of a supergiant, watching a massive convective plume condense into a dust cloud that triggered a global false alarm.
But which ultimately trained a specific team on how to observe this exact tricky system.
Yes. And we followed the predictive power of celestial mechanics, calculating the exact window of maximum elongation in December 2024.
And finally, using advanced coronagraphs, adaptive optics, correcting atmospheric turbulence thousands of times a second, and months of angular differential imaging algorithms to digitally strip away the diffraction glare. Human engineering pierced the veil.
We finally saw it.
We didn't just find a tiny rock, we confirmed a massive 3-solar mass star hiding in plain sight.
It is a profound reminder that our models of the universe are constantly subject to revision. The cosmos is inherently more complex and more dramatic than our initial assumptions ever allow.
So the next time you step outside on a clear night, allow your eyes to adjust to the dark and look up at Orion's right shoulder. The relationship you have with that ruby-red point of light must change.
You're no longer looking at a solitary, dying giant quietly waiting to collapse.
You are witnessing a high-stakes gravitational dance. You are looking at a system actively exchanging mass, altering its own fate across the centuries.
It's beautiful and terrifying at the same time.
Completely. Consider the reality of that impending explosion. When the core of Betelgeuse finally fails, when the outward pressure drops and the shockwave tears through the hydrogen envelope to light up our night sky, whether that happens tomorrow or 100,000 years from now, we won't just be watching the death of a single star.
No, we won't.
We will be witnessing the violent, chaotic, and incredibly complicated climax of a cosmic relationship that managed to stay entirely hidden from human eyes for 100 years.